Today I'm going to discuss time reversal and spin, an odd property of particles. These are both mysterious topics in physics, and that can mean only one thing. We don't yet have the right math. So in this show, I will show you some of my new math tools for dealing with these, which I think take a step in the right direction, although I don't ever completely understand anything that I do. So there is an arrow to time. I can't remember the future, but I can remember the past. Why is the past different from the future? Well, if you look at the laws of physics, they don't give you the answer, because the laws of physics are time symmetric. If clocks were to go backwards in time instead of forwards in time, the laws of physics wouldn't change one bit. And if the laws of physics don't care, how can anything else? Well, actually, there is one law of physics that cares. It's called the second law of thermodynamics. It says that our measurement of how random things are increases over time. Physicists and people who are very good at logic have taken a good look at the second law of thermodynamics. This entire book, Time's Arrow and Archimedes' Points, is devoted solely to this one topic. Why does time have an arrow to it? And what people have concluded is that it is put in by hand. There is no good why. It's just the way it is, and deal with it. Which strikes me as very odd, because the direction of time seems so clear to me. There's so many examples of things that show that time has a very obvious arrow. So I want you to watch this next little clip from the Stand-Up Physicist archive and see if you can tell whether time is going forward or whether it's going backwards.
All the girls in the classroom think he's hot. He shows up wearing the sandals with the white socks. He hears them giggling while he's got his back to the class. He thinks he's got an eraser mark on his ass.
Hopefully, it was really clear whether time was going forward or in reverse. So, I think we need to understand why this is a problem in standard physics by looking at their math. One of the best things about this show is that it forces me to do things that I feel uncomfortable about doing, but I have to. So I wrote over here space-time reversal. I really didn't want to include the word space, but I had to because of the math, which is contained right down there. That is a member of the Lorentz group. A group is a collection of objects that can kind of transform between each other and they just hang together. And this particular member of the Lorentz group, it changes the sign of time. So it goes from a plus to a minus. And that's what that first one does, that first -1. But you'll notice that there are 3 other ones. And what they say is space, stay in place. So the tool for doing reversals of time also necessarily must make a statement about space. So the math tool says as directly as a math tool can that you must operate on time and space. Now that we are forced to always use the word space-time where we used to use the word time, I look at these two clocks kind of differently because they actually have cosmological impact, as in how the overall universe works. Because now I see these things ticking, and what do I see increasing? I see space-time increasing. Now, I have what's called a low relativistic velocity to this clock. We're traveling together. And so when I look at this clock, what I see mostly, in fact almost exclusively, is that time is increasing for that clock because we are traveling together. But if I had a really powerful telescope, I could see parts of the universe that are running away from me at nearly the speed of light. They don't like me. They don't like you. And for them, they're giving us a message. And the message is similar to this. It says space-time is increasing, but it appears to be space increasing for objects running away from us. So whether we look at galaxies or this clock, we make the same conclusion. Space-time is expanding. But if you have a low relativistic velocity, you're traveling with me, it looks like time is increasing. And if you're running away from me, it looks like space is increasing. If I have a couple of events and I want to reverse them, I use that element down there. And if I want to reverse the reversal, we started like this, ended up like this, and now I want to get back, I use the same tool yet again. So forward exactly equals going backwards. And this is the reason there is a problem with the arrow of space-time. Because if you use the same tool to do both operations, the laws of physics are going to look the same running in reverse as running forward. There's another problem with global transformations. And that is, I don't think they make sense on physical grounds. Let's say my fist here was an electron. And here I got a photon. And the photon's wandering around. And something that's very common is that a photon gets absorbed by an electron and then lets go. That looks kind of like, well, the reverse would be it goes here and then it goes out. Looks very similar. And this happens all the time, you know, this sort of thing. But let's just imagine a different situation. You got an electron, you got a photon, and it goes boom, and it hangs out for like 1 billion years. I'm not going to wait that whole time. We're going to just chop out most of the time in there. And then it lets go. Well, according to our current math, we'd use the same tool in this situation, which seems absurd. One should be really simple, and the other should be so complicated it's like impossible to actually work out. But with global transformations, that's not the way it works. So I'm going to introduce a new math widget to do space-time reversal. One quality that I want, without a doubt, is that going forward is not quite like going backwards. And I want to get rid of this global transformation stuff. I want to make things local. All right. Why local laws? Well, some of the most important laws in all of physics are local already. There's something called the Standard Model, which is where all the fundamental particles kind of come from. That's a local law. and general relativity, though our best explanation so far for gravity, that is a local law. All my work is with local laws. And the reason I think is because, if it happens here, I have no problem with it happening on the other side of the galaxy, but if it happens on the other side of the galaxy, it can't know about what happened here. So, like politics, all physics should be local. So here is my math widget for doing that. You can tell that this is a local type of transformation by the presence of all those t's, x's, y's, and z's. It looks very complicated indeed. But how does the reverse one work? So if this one will take these two events and reverse them, how do we reverse the reversal? Well, it's actually very similar to this one. In fact, the diagonal will be exactly the same, no changes whatsoever. And the magnitude of all those numbers are also exactly the same in exactly the same spot. What changes is the signs of the off-diagonal parts. What is a plus off the diagonal becomes a minus. What is a minus becomes a plus. And so by doing that, you can get the reversal of the reversal. But it means that going forward is not the same as going backwards. But how do we explain how classical physics really kind of look? Very time symmetric. Well, there you have to consider the sizes of these various numbers that go into this transformation. And the x's and the y's and the z's are extremely tiny. You have to go out 5 or 6 zeros from a decimal point to get to where the x starts having a value. So it's like 1 part in 100,000, 1 part in a million. It's like, forget about it. Let's just call that 0. And when you do that, it turns out that you have zeros on all the off diagonals. And down the diagonals, you just have a -1. So if you want to reverse time in the space-time context, just flip the sign of time and you're fine. That applies as an approximation in classical physics. And that's the key message, that it is an approximation. Because it is an approximation, it's not perfect. So even though they're 1 part in a million, that, those little things add up, if you add up, say, 100 trillion. And since there are so many particles out there, that kind of thing does happen. So the laws of physics kind of do look obvious as far as how they go in time, because we add up so many of those approximations. So it is this asymmetry in this tool right there that I think leads to the asymmetry in time reversal in spacetime. Spin is a property of particles. And if you read enough physics books, they generally say that physics of even spin is easy to understand, but odd spin is impossible to understand. I think both of these are wrong. First, because we don't yet have a good way to understand integral spin. And I think we can show you 2 examples at least of things with odd spin. And those are things that they take 2 times to come around to the start. Let's start with the easy case, even spin. What I mean by that is you start here, you loop around once, and you end up where you started. Now I had to go forward in time but I ended up back where I started. So I say that is 1 time constraint and 0 space constraints. Because I could have done this around the x-axis or the y-axis or the z-axis sort of thing. But I didn't. I also want to demonstrate this with a simple object. And what I always keep around is beer. So if I take my beer can and I do 1 simple rotation, look at that, back where I started. Pretty amazing. Now, if I had done a backflip, I would have ended up right here after 1 backflip. If I did a cartwheel, I would also end up in the same spot after 1 cartwheel. So this is a property of even spin. But how do we do the math? Well, first, I shouldn't drink on camera. First, what you do is you think about rotating around the z-axis. And if you don't like rotate at all, well, you should get back to where you started. And that's why there's that 1 in there. But if you're really good at the algebra, you can show that a rotation around the z is the same as doing a rotation around x followed by a rotation around y minus a rotation around y followed by a rotation around x. Now we're going to try and understand odd spin. Odd spin has the property that it takes 2 times going around to get back to where you started. So we'll try and do this with this little ribbon here. Now, what we do is after 1 rotation, instead of starting there, we just twist it, a little half twist. And the important thing to notice is that we're not back to where we started. Bummer. So let's just continue on that same path that we were. Just keep on follow the blue brick road. Look at that! We are back to where we started by going around twice. So this little, Mobius strip has the property that going around twice gets you back to where you started. How am I going to do this? With beer. Okay, I put it in my palm and I do 1 rotation. Trying not to spill too much. Am I back to where I started? It doesn't feel like I am. So I'm going to do it 1 more time. 1 more time. That feels good. Because my shoulder here put a constraint on the situation. But you know how I had 3 different ways I could have rotated it when I was doing even spin? Now, when I do this thing here, I could continue on, or I could do 1 quick rotation and get back to where I started. But there isn't a 3rd way. There's only 2. So there's something important to be learned there. Don't spill beer. All right. We are going to need to change our math tool to accommodate this. But changing math tools is like nearly impossible. I mean, we're clearly going to need that 1 in there, right? Because if you do no rotation, you should end up back where you were. And we're probably going to need those rotations around x, y, and yx sort of thing. So how can we change this to accommodate this need to go around twice? Well, this is one of the few times in my entire life where I actually invented a new math tool. And the idea was to start with a math tool that is well known. It's known as a conjugate. And what it does is it flips the sign of x, of y, of z. But it keeps time the same. And if you take the conjugate of those r's down there, it doesn't change a darn thing in the calculation. Ends up exactly the same. But remember, we learned something about from the beer. And that was that we had a constraint in space. So I thought, let's try and treat space slightly differently. That's how I invented the first conjugate. And what the first conjugate does is it leaves the sign of one direction of space the same and flips everybody else. And so now we're not treating space all uniformly. We're treating it differently for x than we do for y and z. And for those of you who are good at math, algebraically, what I'm doing is I'm just putting an I on either side of the object and then taking the conjugate. Now the reason this works out is that by putting in that I in there, I basically have two i's sitting in between each r. And an I squared gives you a -1. And the -1 basically makes this a minus and makes that a plus. By doing that, for the smallest steps are in the minus z direction. They're going the wrong way. And so you go the wrong way, you end up in a bad spot, just like we did here, but you keep on going, and you go a wrong way on the wrong way, and after 2 full rotations, you end up in the right way. So, what we need to do, mathematically, if I can fit this in here, something like that, is by taking the first conjugates of our rotation matrices, we can end up with a tool that has this 2 rotation character, the character of odd spin. Everything we've done so far is actually classical in nature. And spin is supposed to be describing things that have to do with quantum mechanics. So you really should see my other video, Why Quantum Mechanics is Weird, to get a fuller appreciation of this. But it has to do with doing calculus on space-time together as a unit. Because to do that properly, at least in my opinion, you have to either choose space to go to 0 first, or time to go to 0 first, and then the other one. So in classical physics, what happens is the space part of change goes to 0. And you see frame after frame of time marching on. So that is the stuff of movies. So here we see 8 stages of beer in the even case, and 8 stages of odd spin beer. But this is classical because it's a movie. To get into quantum mechanics, you use the same pictures, just in a different way. In quantum case, you don't get to watch a movie. Instead, you get to say, these are the 8 states that the beer can be in for integral spin. Here are the 8 states that the beer can be in for odd spin. Now we can take these states and superimpose them. Here is a picture of the 8 states of even beer spin. It kind of looks like you've been drinking those 8 beers, and this is what you actually see. And here are the 8 states of odd spin beer. Now the beer can behaves like it's essentially in all these states until you actually probe and say, which one are you in? And it says, well, I'm in this one, or I'm in that one. But mathematically, it's like it hangs out in all 8 states. What have we accomplished? Well, we've been thinking about some very difficult issues that really are a mystery to physics. And yet, they apply to simple particles like beer. And we now have some ways to dealing with it. For space-time reversal, the key part was including the word space when thinking about time reversal, because space has a handedness to it. And so there's a handedness to time reversal. And we thought about spin, whether it's integral spin or half integral spin. We have ways to visualize them, both classically as a movie and as a quantum superposition of states. So thank you very much.
All the girls in the classroom think he's hot. He shows up wearing the sandals with the white socks. He hears them giggling while he's got his back to the class. He thinks he's got an eraser mark on his ass. And all the girls from the hall show up to hear him talk, even though most of the time he's covered in chalk. Math prof, rock star. Math prof, rock star. Oh yeah. Math prof, rock star. He was young, he never thought that he would be a math prof, rock star. And after hours outside of his office, there's a line waiting, full of girls who want to ask about their quadratic equations. She leans over the desk and twirls a pencil in her hair, complains the grade he gave her was way unfair. And all the professors, they laugh about it and they wish him well. The guys in the class are all just jealous as hell. Math prof, rock star.
I thought I'd teach my little lady all about global transformations. Honey, does this dress make me look fat? No, I wouldn't say fat. I'd say more like a bloated cow. Now that's not as bad as a beached whale, but I'm thinking more bovine with a gas problem. It's just a joke, honey. But I've got my get out of hell free card, which is a global transformation that will get me out of this situation.
And I've got a bat, which is a local solution for your knees.
Honey, can I offer you 3 kilograms of dark chocolate? Chocolate?
Can I offer you
Chocolate?
my stick?
Honey, can I offer you my credit card to use however you'd like to?
I think I'll go for a little walk. But before I do...
Rock star, oh yeah.